Dear stress engineers, hello again. We go through chapter 3. In this video, chapter 3 is one of the longest in the book, and it deals with the interpretation of the results. So let's say we have built our model in the best way possible, then we have applied the boundary conditions in a correct way, hopefully, and we have run the model, and now we have the results and we need to deal with them. So one of the things which one might have to face is the contour of the stress. For example, here we have a cantilever beam. Stress can be averaged at the nodes or can be not averaged at the nodes, and in the two pictures you can see the difference. Here is average, and so we have a smooth contour, and here is not average, and we see that the contour is slightly discontinuous. There are some different ways on how to use this. If we have a shell element model and we have different thickness at a certain point, if we smooth it, the thickness with the higher thickness will lower the stress of the lower thickness, and vice versa. So best way would be to use an average plotting, and this one also, the average plotting, is useful to see discontinuities and is useful to check for maybe distorted elements or some strange things in the mesh, like for example here, depending on what is the reference system that we use to extract the stress. This is the global contour, so the stress is plotted in this reference system, and in this case the stress is plotted in this reference system. It's the element reference system, and we see here that if one element is differently oriented compared to the others, there are quite some strange things here which might happen. So it's important an average will highlight some possible problems in the mesh. Or again, different, like this one is averaged, and we get a strange contour because of this element here. Or again, for different, the post-processor and the code might have different way of using the element reference system, and if the element is distorted, we can have some, again, strange behavior that we won't expect on this simple case. So here it's simple and it's easy to understand, but clearly on a more complex model it won't be so straightforward. Shell elements as well have an additional problematic which comes from the normal. So if one element is reversed compared to the other and we plot the bottom or the top stress, then we can get something like this. If it is not averaged, this will pop up, while if it is averaged, it's not said that we can see it correctly. If we have an I-beam, double T, here made out of shell, the sections here are reported, and we want to know the stress in the 3 points A, B, C, then we might have some surprises at point C, and in the book is explained why. Here the example is treated by calculating the stress by hand, let's say, with the solid mechanics formulas, and also with the finite element code. And it's explained how or why we can get some strange, unexpected results compared to the theoretical ones. This example will be recalled later also with bricks and then also with beams. Another example here is presented like if we want to connect these 3 plates with rivets. First simple model can be done with just one shell because it's a precising. To understand how many rivets and what is the force which would pass through the rivets, here is shown how to use the fluxes in the shell elements. Then a more sophisticated model is done by connecting only the two parts are connected only among the nodes or with the nodes, through the nodes, through some nodes, so that we can extract the force directly from the nodes. And then a more complicated model is the one which sees the modeling of the two plates plus the third one, and then the connection with the beam elements with the section of the rivets that are planned to be used. And here all the three different results are shown. And then also it is highlighted that if we change the way of loading this thing, so instead of being axial or bent in the plane, we bend it out of the plane, then the behavior of the first model is different if we compare it to the one with the two plates, because of the different inertia, and the stiffness will be different. So here it's shown what are the difference that are found. Then with solid elements we rebuild the same beam, and here it's shown that there is no way of dealing with the intersection here, because the geometry is correctly represented by the 3D models. And then again some words are spent on discontinuous joints. So we see here some beams which are connected through bolts, and in this case rigid elements were used to connect the center of the hole with the border of the holes, and then spring elements were introduced between them to extract the force. And then for welded joints, so continuous joints, it is shown that some codes allow to extract the section force by simply cutting through a plane and then asking the code to integrate the stresses and then extracting the section forces to be used, like we see here, for some normatives to calculate seam corner welds, for example. Then again, the same beam is recalled for the third time, reused for the third time. In this case, it is modeled with beam elements, where here the graphical representation is obtained by the post-processor knowing which are the characteristic of the section. So in this case, it is able, the post-processor is able to represent the geometry of the one-dimensional element, and also the stresses can be plotted on the section like this. So here it's said that in the three cases, so shell, solid, and beam more elements, the case is so simple that the results matches. And probably the beam element would have been good enough for this kind of structure. Then a classical example here, it's taken like just a simple T bracket, which is pulled on the center part, and it's restrained by two bolts. So how to constrain this? 6 degrees of freedom, only 3, using only MPC elements, rigid elements, or maybe using beams to extract the forces. And here all the examples are presented, all the cases. Also the prying action effect is explained. Also this example will be reused in the future chapters. Then some notes on graphical post-processing, so using the arrow plot for a tensor quantity can be useful to see the concentrations, to see the flows, how it is going through. And then something which I have found many times in my life, and a lot of people asking what would be the meaning of having a funnel shape of a tube which is under pure torsion, and here is explained why this is happening and how this can be avoided by using non-linear analysis. And then again some notes on strain energy, which can be used to find the areas where we need to reinforce or areas where we need to take mass away. And this is something new for the book itself, is just the explanation on why stresses calculated in the Gauss points are different from stresses calculated in the nodes, and why this Sometimes is useful to know, for example, when we have an perfectly plastic material, as we will see in chapter 13, the yield limit should not be overcome, of course, because that is the maximum, but then the stress is calculated in the Gauss points, and then it is interpolated through the shape functions to the nodes, and so it can be higher or lower. But in the case of a material which is elastic, perfectly plastic, it cannot be higher if this is yield. This should not be higher than the yield, but this is happening. Unfortunately, not all the post-processor available can simply move the Gauss stress to the node. It is always or almost always interpolated. So it's good to know this. And here it's explained how to switch from the Gauss point to the nodes and vice versa. So this transformation matrix is given, and you can do the test by simply using an Excel, using the capability of Excel to deal with matrices. And this is all for chapter 3. So next one will be natural frequencies and mode shapes. So hope to, again, as I said, see you in the next one. Ciao.